And so we thought it would be a good idea to ask Martin to give a little bit of introduction, since this is a fairly close community which developed over, what, last 2 decades maybe?
Yeah, by now it's almost 2 decades.
Yeah. New mathematical tools, these diffeomorphism groups, which in some sense are descendants of the transformation that Darcy Thompson uses in his book, and which Alain showed us, and many of you know from the book itself. Anyway, Martin's got his undergraduate education in Vienna. He's originally from Latvia, but the family moved there. And up to master's degrees with Peter Mihor, who will be here at the workshop next week. And then did his PhD with one of the organizers of this program, Darrell Holm, in 2012, who also will be here, I hope, next week, and maybe give a talk as well. And then he was a postdoc with another participant in GFS program, Tudor Ratu, that many of you have seen here before. And then in 2014, he went to Brunel University as a lecturer and is there, and is, with Darrell, a co-organizer of this workshop. So we look forward to some introductory remarks and maybe also some more advanced topics.
Right. Well, thank you for the introduction. Yes, so this talk is an introduction into what will be discussed at greater detail next week during the workshop, and it will stay mostly introductory. Some outlook into what are sort of the mathematics behind it, but it's mostly meant as an introductory talk. So there are two aspects of the title. There's shape analysis and computational anatomy, and I'll discuss the relationship between them later. And I'll start with shape analysis, and then in the second part move on to computational anatomy. So shape, as a term, shape, so the word shape means many different things. And if you look at the dictionary, then there are several meanings. It can mean the external form, contours, or outline of some object. It can mean a shape as a geometric figure, as you saw in the painting on the title slide, or it can also mean the original form or contours of something, the shape of an idea or so. And as far as the shape analysis is concerned, we are looking at the first definition. A shape is a physical property of an object which somehow determines what is the inside of what is outside of the object. So here we have pictures, and we have then segment outside the shape of those objects. And now what shape analysis is interested in is asking, so how much information about the object is contained in its shape? And if you know about the shape of an object or a collection of objects, what does it tell us about the objects themselves? So it's a sort of interplay between shape and other things that we're looking at shape analysis. Now, in shape analysis, we don't look at individual objects. We don't ask ourselves, well, let's take this leaf, what does its shape tell us about it? Instead, it's a more perspective of we take a whole collection of things and ask ourselves, what can we tell about the collection of the objects? For example, if we have enough leaves of a species of tree, can we sort of say are sort of two distinct species, how distinct are the leaves? Can we distinguish three species by looking at enough leaves of the class? So there are several steps involved in doing shape analysis. The first thing we have to say what we mean by shape. We sort of have to define mathematically what is shape, and there are various ways of doing that. I'll show several of them during the talk. And after we've agreed on a definition of shape, then the collection of all shapes that satisfy the definition forms a shape space. So it's a set of all shapes, and it's a class of objects we're working with mathematically. And this class of shapes usually is an infinite dimensional manifold. And I'll explain why it's both the manifold and why it usually should be infinite dimensional. After that, we need to equip the manifold with some additional structure, be it either a distance or something more complicated like a Riemannian metric, so we can measure things, measure difference between shapes, measure distances, and perform. And then after we have the structure, what we then are interested in doing is doing statistical inference. Use that structure and our notion of shape and some actually measured shapes to then make a statement about variability, where's their about their mean, and etc. So those are the 3 steps. And let me explain in detail what's sort of happening in each of them. So the first is why do we need nonlinear notion of shape? What is it? It essentially means that for shapes, addition of shapes is not a meaningful operation. Because usually a shape, we don't have, a shape is almost never uniquely represented by some mathematical object. There are always several objects, either being the landmarks or curves, that represents the same shape. And the simplest example is we usually are not interested in the absolute location of an object, so it's sort of always undetermined up to translation, and almost always also undetermined up to rotation. So we take, let's say, these curves and we translate and rotate, and sometimes also change size, but we want to say that they represent the same shape, so they're always equivalence classes. And as soon as you go to equivalence classes under a certain class of transformations, you lose linearity. A simplest shape space, a finite dimensional one, and the first that was widely applied is the space of landmarks. So we take some biological specimen, let's say skull, and we put points of interest on the skull, finitely many, based on either biological principles, like where the teeth are, or there are complicated Latin names for that, or based on mathematical principles, like say furthest point to the right, or this point looks like it's exactly the middle between point 8 and 10, or along points of greatest curvature along the outline. So we put identifiable landmarks on a shape, and we do that for each specimen, and then we compare the position of those landmarks. And again, we're not interested in the absolute position, and we're not interested in rotation, and often in this kind of analysis, one is also not interested in scale. So what happens mathematically, we represent an object by k points in the plane, or higher dimension is also possible. And so our space, we start with a space r to the power 2k, which can be identified with k copies of the complex plane. We normalize the points with respect to translation, so we subtract the first point, and then we end up with in c to the power k minus 1. And normalization with respect to scalings and rotations, well, scaling and rotation is just multiplication by a complex number. So we identify 2 k minus 1 tuples of points if they are related by a multiplication by one common complex number. And if you look at those equivalence classes, that's exactly the complex projective, well, k minus 2-dimensional complex projective space. So in this, so representing objects by k points, and then quotienting out translations, rotations, scalings leads to the notion of shape space, which is mathematically the complex projective space. So that is Kendall's shape. And of course, because we do natural operations starting from Euclidean space, this space then also has an actual distance, an actual Riemannian structure, and so on. So this is one example of where sort of nonlinearity comes into play. A nice special case is if we have 3 points, well, 3 points define a triangle, and if you have 3 points, so k equals 3, then we get a CP1, and CP1 is diffeomorphic to the sphere, and what we see here is the sphere flattened out. So this is the North Pole, the green line is the equator, and the outer rim is that's all the South Pole, so it should be sort of imagined glued together. And what we shown here is each point on the sphere represents the shape of a triangle. So we start with an equilateral triangle. Here we have at the North Pole we have equilateral triangles as the South Pole, but just with flipped orientation. Along the equator, and then as we move from the North Pole to the equator, the triangles get flatter and flatter up until we have the degenerate triangles along the equator, and then the sort of same happens in mirroring at the bottom. So this is shape space of triangles. And for that one has explicit formulas for distance. Yeah. So that's finite dimensional shape spaces. Now, why do we need infinite dimensional? Well, often, so in this case, landmarks make sense. There is biologically meaningful places where to put landmarks. In other examples, there is not.
Just
Sure.
a stupid mathematical question. So is the projective plane always diffeomorphic to a sphere for any dimension? Or are there, well, if you go to higher dimensions?
No, just CP1.
Just CP1?
Yeah, no, the CP1 is a special. Is a nice special case. Also, when you get landmarks in three-dimensional landmarks, and your quotient delta rotation group, that is also not a projective space anymore.
No,
It's
because,
just
you need to remove.
you need to move all of
It's rotated. Well, it's only when you remove scaling that you get.
and when you remove scale, yes, and also when you remove scale.
So in shape analysis, just to make sure, size is never of interest.
It is. It depends what you want. So you can remove size. You don't necessarily have to. It depends very much on your problem. We will see later as a sort of the diffeomorphic methods. They don't remove size actually. And
So you just take W on the circle in that case.
Yes. Yeah. For example. Yeah. You just take W on a circle and you keep size information. Yeah.
So at the north and south pole, you have two triangles that are the same, except the orientations are flipped.
Yes.
So is that a meaningful distinction?
Again, it depends on your application. Well, if your landmarks are it depends if your landmarks are labeled or not. If you have point A really corresponds to point A and point B corresponds to point B, then yes, so you have point A, B, and C, or point A, B, and C. I mean, yes, it might be a meaningful distinction or it might not. Again, it will depend on your application. If you have just an unlabeled set of, if you have sort of points, if you don't know a priori what their correspondence is, then you would want to also quotient out that relationship. And you get, again, a different notion of shape space. And as they're related, but I mean, mathematically, they'll be sort of, it will depend on application what exactly you want. Right. So, in some cases, landmarks make sense. Other times, you have a shape, and it's sort of difficult to see where do we put landmarks. Well, we have the tip, and we have that tip, and then we have this outline. And where do you put landmarks, such that when you take a second feather, that the landmarks have a meaningful correspondence between the two. What you really have is just the outline. What you have is a curve. In a way, infinitely many landmarks. A similar example, you take stone tools from the Stone Age, and again, you have an outline, but there is no obviously meaningful way to place landmarks. And you can, well, one way of dealing with it is say, okay, so mathematically we say our shapes are these images of curves, and if we say that, then our space becomes a space of all curves, which is an infinite dimensional object. Now we can of course also take some other position to say, okay, yes, ideally they might be, but when we do any computations, we do some, well, we need to work with finitely many points because that's all our computers can do. And well, the counter argument to that is, yes, but how many do you put there? Do you discretize that with 100, 102, or 100 or 200 points? And you would like your result not to depend on that strongly. So you want to have the theory behind it that says there is something meaningful you do with the outline, and then yes, you make some discretization error and you do approximation, you compute, but you have a result that ideally should correspond to something which only depends on the outline. And that's the theoretical justification why one should bother with infinite dimensional shape spaces. Right, and I'll talk about the shape space of curves as sort of simplest infinite dimensional space in some sense, a little bit in more detail. And then after we have our infinite dimensional manifold, or possibly finite dimensional manifold, then the next question is what sort of structure do we put in it? And the simplest structure is, say, we just put the distance on it. What is the distance between two shapes? And there are all kinds of distances. There are things, I mean, well, if you have landmarks, then we have in a way, canonical distance. If we have curves, there are things coming from topology, Gromov-Hausdorff distance. One can interpret curves as currents and use ideas from geometric measure theory to get current or varifold representations. One can use diffeomorphisms, and I'll talk about that later. So there are all kinds of ways to define distance. There's no canonical choice. And the question of what you choose sort of depends very much on the data you have, etc. But what I'll be more interested in is putting some more structure, not just the distance, but having a Riemannian metric on it. Just to use also the fact that we have a smooth manifold structure of our shape space and to put a Riemannian metric on it, which then also defines the distance, but also gives us in a way, canonical coordinates using the Riemannian exponential line. Okay, so let's look a little bit about the manifold of curves. So the basic object is a space of smooth curves, and we assume they have nowhere vanishing parametrization, so the derivative is non-zero, and we call that space Im, which is short for inversions. And this condition here is an open condition, so this is an open subset of the space of all smooth functions, and any open subset of a vector space is in a canonical way a manifold. And the tangent space is geometrically infinitesimal deformations of a curve are sort of vector fields along the curve. Actually, this is represented here. So we have our manifold here, and each point of the manifold is a curve, and paths on the manifold are deformations of curves. So you go from one point to another, but sort of smoothly deforming the curve along.
And you allow self-intersection then? You haven't...
Again, it depends on application. So immersions allow self-intersections. So there is nothing that prevents you from there. You can restrict yourself to just embeddings to prevent self-intersections. And again, we'll sort of, there are Riemannian metrics that prevent self-intersections. There are those that don't care about that. There are, yeah, it sort of, again, it depends on what you want.
So in 3D applications,
yes,
your inversion will be more complicated. Simple sphere
yes.
won't work for shapes, right?
Yes, yes. So both landmarks, yes, it will not be a sphere anymore. And also you can look at curves instead of curves in a plane. You can look at curves in space. You can also look at similarly the space of surfaces in R3. So yeah, it's all of that is possible. Right. So you have a space at each point is a curve, and then a tangent space sort of represents infinitesimal deformations. So it sort of shows in which point you deform each curve.
And you curvature condition, you see prime, it's just so that you're able to define a tangent vector at all points?
The C prime is, okay, I'll come in a moment why C prime. The C prime is because really what we're interested in is not in the parametrized curves. We're not really interested in the parametrization. So we want to quotient out the parametrization. And to do that, we want this non-degeneracy condition. Because, I mean, each geometric when we have a geometric shape, there is no a priori parameterization to that. And so we model it by saying, okay, we only look at regular parameterizations that don't stop at regular. And then that we can quotient out and we get the notion of a smooth manifold out of that for the quotient space. Right, but before we pass on to the quotient space, what kind of Riemannian metrics does one look at on the space of curves? Anyways, the simplest Riemannian metric is an L2 metric. So again, so C is a curve, H and K are tangent vectors to the curve, so vector fields along the curve, and an inner product is the L2 inner product between the functions, between H and K viewed as functions, and we weight it by the norm of by the length of the derivative C prime. That's an L2 metric. We can also add derivatives of H and K. So we have the L2 part and we add derivatives of H and K. And we have a weighting factor, and I'll explain where the weight comes from. We can have something that is scale invariant by adding appropriate weights with respect to lengths here. So again, it's a possibility to get length invariance or not, depending on needs. And basically, well, inner products on the space of functions gets you to the, well, are inner products of Sobolev type. So you sort of get, that's where you get connection to functional analysis and analysis in general. Now, where do these weight factors come from? The weight factors come from the fact that, yes, we're not interested in a curve as a function from the circle to RD. What we're really only interested in, what shape does it describe? And two curves can describe the same shape, and they do that if and only if they are related by a change of sort of relabeling of points on the original circle. So they're related by a different. So shapes are really curves, equivalence classes of curves under this equivalence relationship. We can show that represented here. So up here we have the space of curves, and down here we have the space of shapes, represented by the fact that we have no color information here, what we do here. And here, as we move along, so above each curve, we have the fiber of all the different curves that represent the same shape, and as we move transversal to the fiber, we change also the parameterization. And this space here is the quotient space of smooth curves under the actual diffeomorphism. And the state, there is a theorem that states that this quotient, well, not quite this quotient, we have to restrict ourselves to a certain nice class of immersions, is also a smooth infinite dimensional manifold. Now this space here, that was an open subset of a vector space. We can add immersions, and if the immersions are small enough, then we stay with immersion. This quotient space, this is truly nonlinear. So that's again where the nonlinear nature of shape space comes into play. And to get a Riemannian, and this is a space we're interested in, and to get a Riemannian metric on this space, what we need to start with a Riemannian metric up here that is invariant under the group action of the quotient alpha. And so to get the invariance under the reparameterization action, this is why we need the weighting terms in the definition of our inner product. We cannot just take the L2 product with respect to the parameter theta. We need to weight it by the curve to get the invariance. Now, analysis plays a role, and one reason where we can see why analysis plays a role is by looking at properties of the L2 metric. Which this is the simplest kind of metric. You just take the L2 term, and you need to add this norm C prime to get reparameterization invariance, which one can see with a simple calculation. If you reparameterize the curve and those tangent vectors, then this part norm C prime gives us a phi prime, and then a change of variables removes all the phi's. As a Riemannian metric, it has a geodesic equation, and a geodesic equation on the space of curves now becomes a partial differential equation for the two parameter family, so C of P and theta. So we have the curve parameter, and we have the sort of the deformation as a deformation parameter. And one can calculate this equation here. And ds is the arc length derivative with respect to the curve. And even and it's as far as I know, it's still unknown whether this PDE as a PDE is locally well-posed or not. Whether it has local solutions that depends continuously on its initial data. But we can look at geodesic distance induced by this metric. So we take two curves, we fix two curves, and we look at all the paths connecting these two curves. Each of the paths has a positive length, and we look at what is the infimum over the length, and we want that to be the distance between our shapes. And
sorry, can you explain where this geodesic equation comes from?
It comes from taking the so you take the energy of a path. So C is a path, d theta, which is integral over the Riemannian metric. So the length of the velocity vector squared, and you take the first variable, you take all of the Lagrange equations of that. That's a geodesic, which is critical points of the energy of the path. And in finite dimensions, you have just the time variable and finitely many coordinates, and then you get an ODE. Here you have the time variable and infinitely many coordinates, and so you end up with PD.
What's d sub s?
D sub S is the arc length derivative. Yes, that's what we're going to define. D sub S is so D sub S of H is 1 over norm prime H prime, and well, C is the derivative with respect to the curve parameter. So, now we can look at the geodesic distance between curves as looking at the infimum or either the length or the energy. And the surprising result is what happens here is that this geodesic distance is identical to 0. So no matter how different the two shapes, the two curves are I start with, I can find arbitrary short paths between them. Now, no path will have 0 length because this is still a positive definite distance, but I can find arbitrary short paths between them. And this is true both on a quotient space as well as on the space of inversions itself.
That's due to the choice of the L2? Yeah, that's
This is due to the choice of L2, exactly. This is because we L2. As soon as you go add first derivatives, you go to H1 or higher, this stops happening. But
because you don't penalize the velocity along the curve.
Yes. Yeah. So L2 is it vanishes, H1 is positive definite. It gives you a well-defined notion of distance. What happens for the Sobolev orders in between, so fractional order, it's unknown where the cutoff is. I would conjecture it's 1/2, but
Because it's between 0 and 1?
no, because of the diffeomorphism group in one dimension, the cutoff is 1/2. But for curves, well, yeah, also. Yes. So there are sort of analysis does every now and then sort of rear its head and sort of tell us something that things that we should or should not do. And yeah, if one try to use this metric numerically and just implement it and try to find minima, one would see things degenerating quite quickly. Which is, as far as I know, anecdotally, how this result was found. Dave Mumford did try to compute things numerically and saw the numerics behaved weirdly, and then started looking into it and discovered that it does in fact vanish. Okay, so that's a little bit of analysis that sort of happens, and one can also do analysis for the H1 metric and H2 metric and so on. So interesting questions and interesting results. But let me talk a bit more about applications. So what do we want to do with those things, with these Riemannian metrics? So one thing we want to do is calculate shape averages. So we have a collection of shapes, and in this case the shapes are surfaces, cylindrical surfaces. There is no bottom, in fact. And we want to sort of, if you have a class of shapes, we want to say, so what is a shape, what is a typical shape in this class? And the notion of the Frechet mean in every metric space is one notion, one thing one can compute, and which provides a meaningful summary of the information one has in the class. If we have that, we can then try to generalize the idea of principal component analysis from linear space to nonlinear space. We have a collection of shapes, we calculate the mean shape, we linearize our space around that mean shape using our Riemannian normal coordinates, and then in the tangent space we perform principal component analysis. And then map the results, again using the Riemannian exponential map, back to the original space. And so this is, shapes are shapes of cell nuclei. So the collection of 87 cells. And we perform the analysis using one of these Sobolev metrics, a second order Sobolev metric of the same kind of family I showed before. We calculate the mean shape, and the mean shape is here in bold. And what you see here are the principal directions, principal modes of variation. So the first mode of variation from the mean shape, it's a geodesic in the principal direction. We have the elongation or shortening, then we have a bending motion here, and then the other modes get more difficult to interpret, are sort of more waveforms. But the first two modes, even though they come from this sort of quite removed analysis, not really based on physical principles, one still recovers, one still sees some physical interpretability in the results. The next thing, so principal component analysis is one thing we want to do. Another thing we may want to do is regression. So we have, let's say, brain scans from patients at given ages, and not necessarily the same patient, just different ages. I want to see, okay, so what is average trajectory? What is, just as in a linear regression, I want to see what is the average trend, so we want to find a geodesic that fits as best as possible through our given data. Obviously, whilst not hitting anyone in particular, but yeah, describing them as well as possible. Or we want to move information across our shape space. So we can have a longitudinal studies of one patient imaged at different times. So we have scans at various times. We have the same for a second patient. So we have trajectories, and we want to compare them. And again, because we're in a nonlinear space, comparing things living in different tangent spaces is a non-trivial matter. If we have a Riemannian structure, or if we have a connection, we can use parallel transport to move things between different tangent spaces to a common template. Yes?
Do you ever make connections with things like machine learning? I mean, because here it looks like a,
I was going to
Let's
put
say-
that up in the open questions and sort of future directions slide at the end. Yeah, I'll talk about that at the end. Yeah. Right. So that's the sort of applications one looks at with these techniques. Right. So that was shape analysis. That was the shape analysis part. Now let's go to the second part of my talk, computational anatomy. So computational anatomy comes from, really started in 1908 with the, well, around the 90s. Let's put the name in it. And basically where it comes from is the fact that since the 1990s, we have a lot more images at our disposal. We have MRI, we have computer tomography, and we can take images of patients in. We don't have to rely on anatomically prepared sections. We can take images in a non-destructive way. We have lots of images. We can look at population instead of single specimen, and we can use computers to create generative models than just describing what we see. And sort of all that leads to, well, computational anatomy, which is really the idea of computational anatomy is to create mathematical and statistical methods to model and then analyze anatomy and anatomical shape. So the relation between shape analysis and computational anatomy is somehow, there is an overlap, and then there are things that are separate. Both are interested in describing shape and information that's contained in shape. I would say that computational anatomy is focused on one specific application, and maybe specific is the wrong word, it's still a huge field. Anatomy is a large field. While shape analysis does not necessarily restrict itself to anatomy. On the other hand, computational anatomy doesn't really care that much about what tools it uses. I'll talk about one tool in specific, which has quite a lot of geometry behind it, but if things work, they're happy to use or whatever. And because they know that there is one concrete application in mind, so there's a lot of connection with biomedical engineering and medical schools and so on. While shape analysis is sort of more, in a way, indeterminate. So,
Is it fair to say that computational anatomy is a kind of shape analysis?
I would probably use the Venn diagram picture of that. I think I would say there is an overlap, and what exactly is the size of an overlap is that's a matter of debate. There are other applications of shape analysis that are sort of not medical related. You can analyze all kinds of data, and then there's functional data analysis, etc. And there is a large part of computational anatomy which sort of has to deal with the fact that MRI images are noisy and a lot of engineering type things and sort of the medical side of things that shape analysis doesn't really contribute much. So I'll use that picture to describe that. Yeah, so the question one asks are sort of similar. We want to look at statistical analysis of organ shapes, describe how much variability is there in nature, in normal healthy anatomy and also in disease anatomy. We want to model changes of organ shape, both fast changes as you have in a heartbeat or in the breathing motion of the lung, and also across longer time scales, such as in growth processes or aging, for example, shape changes in the brain as a function of age. We want to, well, the general goal of anatomy is to connect form and function. And some, well, for example, for joints and bones, or for the heart where you have muscle fibers, the connection is quite physically motivated, but we also want to find these connections where there is less physical understanding, for example, in the brain, where one has neurons, but there is something going on as a whole organ level, although it's not quite understood what exactly that is. And yeah, we want to understand what is the difference between healthy and disease. Where does the line lie, and how can we distinguish between that? Right. That's where we get to Darcy Thompson with the famous fish image. The paradigm of computational anatomy is to describe changes of shape using deformations. So if we have two different shapes, and in computational anatomy, shapes are usually volumetric MRI or CT images, or they can also be just planar images. We want to describe the change from one shape to another by saying, okay, how do we have to deform this sort of the underlying space such that the image gets deformed with it. And the motivation from that is already contained in Darcy Thompson's work, which says that in a very large part of morphology, our essential task lies in the comparison of related forms rather than in the precise definition of each. And the deformation of a complicated figure may be a phenomenon easy of comprehension, although the figure itself might be analyzed and defined. So if you have two images that are similar, the deformation between them might be simple, even though we don't have a model to describe the image itself. Now, of course, this picture cheats. I mean, the fish is not created by the deformation of that, but that is okay. We don't, when we take images of different patients and we want to deform one into another, there'll always be imaging, acquisition noise, actual changes in grayscale because of different anatomy, things like tumors, etc. So we will never have perfect thing, but we can hope that the deformation captures the relevant differences in shape, which are relevant but not sort of, doesn't overwhelm the analysis. So the basic object, so basic procedure in computational anatomy is image registration. If you're given two images, and here's our grayscale images, we are looking for a deformation, an invertible, smooth transformation of the underlying space such that one image gets transformed into the other one. And here we have example of this deformation. So that's, and finding, if we can find such a deformation, then we can do things with it. We can map images to a common coordinate system if we choose it. An atlas, and each image can be represented in that. It can be related to that common atlas. So we then have point-to-point correspondences without having to manually label them. If we have then labels, so if we have a segmentation of one image, we can use our deformation to propagate it to the other image. And because we have a deformation, we can look at, for example, the Jacobian to see whether we have local shrinkage or local expansion, things that we wouldn't see if we compare global measures like the total volume. And so that's a paradigm. We choose a template image and we represent variations in images by finding a deformation that changes this template image to our given ones. Yes?
How do you deal with non-uniqueness?
That's the next slide.
Okay.
Yes. How do you deal? Yes. So two things that you have to deal with. The first fact is that there is not a unique deformation. We deal with that by solving, by finding the one that is closest to that entity, that sort of deforms the least to get the job done. For whatever measure of least I put on them. The second thing we have to deal with is the fact that two images will, on average, will in general not be diffeomorphic to each other, because for them to be diffeomorphic, they have to have exactly the same topology of their level sets. So we deal with that by the fact that we don't solve the exact matching problem, but we have an inexact term. So we sort of balance how complicated the deformation is to how well it approximates the image. And again, with for some measure of image this is often taken to be L2.
What's
L2
sigma?
norm. That's a weight factor. You have to balance them somehow.
Is there a good reason for L2? I mean, a lot of times the constraint you want it to be L1 for practical reasons.
So here,
So this
you want
sigma,
to
this sigma doesn't have a geometric or other interpretation. It's just a trial and error type of thing.
yes.
Trial and error to achieve what?
To look and see if it looks good or not. If it doesn't look good, you change sigma, then try again.
Yes, to some extent, yes. Although, as far as I understand, the sigma is less sensitive than other parameters that are hidden inside the D.
Can we interpret sigma as some kind of Lagrange multiplier?
Again, you
Sigma
Yes.
like Lagrange multiplier?
Yeah, that's my question.
but yeah, the thing is, you really don't want to solve the exact matching problem. You really want to take into account the fact that things are noisy, that things are never in perfect diffeomorphic agreement with each other. So it is, I mean, yes, the Lagrange multiplier method will give you a similar formulation, but you really want to find the right balance between how complicated deformation is to how much noise you tolerate in a way. Sorry, L2 versus L1. No, I'm not aware of any of I think L1 being tried. I mean, one thing you want to actually calculate to find the phi, well, you differentiate and you sort of do some gradient descent type methods. I mean, I think that's where L2 originally came from, but I'm not aware of. I know people, when you have different, so L2 is, if you have different image modalities, you have different grayscale values don't make sense, so you can use things like mutual information to account for that. But yeah, yes.
So you mentioned the need to introduce this a possible mismatch due to topology.
Yes.
But if the topology is the same, do you really need
If
such a
you
possible
take,
mismatch, or is it more related to shapes that are not differentiable? Like if you want to have a square and the ellipse, for
in
instance,
practice, right,
there you would, or close to a square.
sure. So so yes, I mean, for example like this, you could expect perfect matching, apart from the fact that these sharp corners will really make you problems. And depending what exactly your energy term is, this might be difficult. But in practice, as soon as you have like proper grayscale images, things like that, you will never have the same topology. There'll be noise that will.
Okay, so I see. Well, if you want to account for
Yeah.
a grayscale, well,
Yes,
and-
yeah,
and
and
image-
that is sort of the
okay.
goal, and there you will have no perfect matching. Right. So this is the second form, and then we have to say, okay, so what is D? And again, there are different choices, and one choice is to say we measure the distance of the diffeomorphism to the identity by asking by looking at vector fields, time-dependent vector fields UT, that generates the diffeomorphism as a flow, and measuring the, in a way, kinetic energy of this vector field with respect to some norm H. Yeah, and then this is optimization formulation that we want to solve. There are various choices of vector fields. For example, we can use H1 norm, L2 plus some alpha times the gradient. If we do that, we can rewrite the norm by using integration by parts into this u dot u times Lu, where L is this differential operator u minus alpha squared Laplace. And we can write it in terms of if we call define Lu to be m, then we can rewrite it in terms of the variable m, which is the momentum, where we use the Green's function of this differential operator. So we can sort of look at it from the other way around. The reason for doing that is that as long as we can replace this Green's function by other kernels as long as they satisfy some positive definity condition. And popular kernels in applications are Gaussian kernel or Cauchy kernel.
What's alpha?
Alpha is a length scale parameter. That's one of the parameters that comes up and that does play a role. Informally, alpha tells you how far points are correlated. Alpha tells you how concentrated the Green's function is. Let's say the smaller alpha, the faster the Green's function drops to 0. And so the smaller you choose alpha, in a way, the less you penalize diffeomorphisms that sort of make rapid changes.
So you fine-tune alpha for applications?
Yes, to some extent, yes. It is something that you need to choose in applications. As it has to, well, it depends on the size of your image, how much noise there is, how much shape change there is, how much shape change you want to capture in your diffeomorphism, and how much shape change you sort of say, okay, this is just noise, and I don't really know what's going on in there anyway. Yes.
This alpha roughly the diffusion coefficient.
Oh.
The heat equation.
Yeah.
Something like that.
Yeah.
You're right.
I see.
So the smaller effect will be less, bigger.
Yeah, in a way you can think about alpha is sort of how far do points see each other's movement. When you get sort of past sort of length scale, the points can move sort of almost independently, and it will not be penalized greatly. And if the points are too close compared to the length scale, then if they want to move in opposite direction, it will become very costly, and hence it will not be permitted because the cost will rather be absorbed here. So that's it there.
And if you take alpha equals 0, it's become ill-posed because you have very fast change that are allowable.
Well, if you take alpha equal to 0, then you end up with the L2 metric, and that has again 0 geodesic distance, so every shape change is essentially for free via a very contorted path, which will break your
So it
reverse.
could be infinitely contorted.
Yes. Right. Now, this method of doing image annotation is known under the acronym LDDMM, which stands for Large Deformation Diffeomorphic Metric Matching. And the explanation for that is a large deformation is because historically, the first ways of modeling deformations was by just adding, say, displacement vector field, which of course wouldn't guarantee you that the result is diffeomorphism, whilst here one generates diffeomorphisms as flows of vector fields, which gives you the diffeomorphic part. It has a metric part because this kinetic energy on the vector fields gives you a notion of distance between deformations, which you then use for the shape analysis. So you encode your image differences in the diffeomorphism, and then you have the distance on the diffeomorphisms to do your analysis.
And matching?
Sorry?
And you didn't say anything about the matching.
Well, matching is you take two images and you match one to the other. Right, yes.
In your large deformation model, the determinant of the Jacobian
Yes.
phi must be kept positive.
Well, because you start from the identity,
That doesn't help.
wait, the determinant,
Otherwise, you don't allow penetration of the material into itself.
but because you have,
Nonlinear elasticity, this is the restriction.
but your deformation is generated as a flow of a vector field, and this flow of a vector field is a diffeomorphism, as long as the vector field is continuous.
So that implies determinant positive or not.
It prevents it from going 0.
Yes.
Because you look only at the space of diffeomorphism.
Right. Okay. So I've asked 5 minutes. So I'll skip some of it. I'll talk about open questions. Right. So one thing. So there's the two aspects I talked about: the shape analysis and the metrics defined directly on curves, and then the second part, which was based on diffeomorphism. One can show the differences as in the first part we had a curve or a surface, and we defined deformation. We just looked at deformations of that object, and we measured its cost and energy. Whilst here we imagine our object to live in some ambient space, and we deform the whole ambient space, and we just look at object flowing through there. I talked about images, but when you talk about diffeomorphisms, so in this representation, the diffeomorphism can act on anything that a diffeomorphism can act on. It can be landmarks, curves, surfaces, it can be densities, tensor fields. So anything can be matched diffeomorphically, provided it lives in this ambient space. So there is flexibility in that. And so here it's surface.
You also allow for a structure to be defined on the surface, in the computation, in the right case, the computational anatomy case.
Yes. Yeah, you can, so this, so the formulation says you have to deform the whole ambient space, but one can, in the LDMM framework in particular, reduce computations to just having to do things on the surface, using the underlying geometry. In fact, the momentum on the surface determines everything in a way. So yes, there is a reduction happening if you're only looking at things of positive, of sort of smaller dimension inside your space. You don't necessarily have to compute everything. Right. Open questions. So what are the sort of things people are working on at the moment? So first is extending the boundaries of diffeomorphic shape analysis. So the diffeomorphic framework is quite useful because it sort of simplifies having to explain the whole shape to just explaining shape differences. But sometimes it's not quite enough, and sometimes one sort of hits it. For example, you have the motion of a lung which slides inside the rib cage. So you have this, yes, there's no sort of tissue breaking, but you still have this sliding motion which is not quite diffeomorphic. So you want to have a model that accounts for that, and some effort has gone into that. As soon as you have like proper changes of topology, for example, a tumor growing out of nothing, then a diffeomorphic model is not enough to capture that. And the question how to combine diffeomorphic and non-diffeomorphic changes, that's still pretty much open.
Can you do a level set approach? That's what a lot of people deal with that. You just look at a higher space and the shape is defined as the intersection of a level set of the...
Yeah, I think
and
the
then
idea
you
is
can do continuous change of that.
Yeah, possibly. I think that, well, so what I mentioned by open is you still want to have part of your shape change encoded in diffeomorphism. And then you have this other part which is sort of the non-diffeomorphic part. Now the difficult question is how do you write down a mathematical sort of an inverse problem that balances it correctly, that gives you the things that you want in the diffeomorphism and the other things in the other part without having a mind of its own and still being reasonably computable. So that balance is tricky. Also matching multiple shapes. If you for example, the brain, you decompose it into the sort of smaller structures and you want to match them. If you do a diffeomorphism, then depending on the length scale you choose, the deformations can be too rigid or not. And if subcortical structures want to move in different directions, you have to try to account for that is sometimes not easy. Finding principles to choose the parameters in there, things like sigma, the length scale, all these methods are not based on physical principles because partially there is no physical principles that changes the brain of patient A into brain of patient B, but you still have parameters in there that you need somehow to choose. Yes, so computational anatomy, neural networks, and deep learning, that's...
What if you do have a physical principle that
Then
of patient A that has a trauma and his brain changed to same patient A but later in time?
Then you would use then you would probably want to use a physical model.
Are there a combined approach where you have physically
I think, I mean, I
physically
believe
motivated data-driven approaches? That's what I mean.
I expect for the heart there should be something where you have muscle fibers and you know physically how they, if you know the orientation of the muscle fibers, you can build a model how it contracts based on incompressibility of
No, this model exists for normal biomechanics.
Yeah.
The question is now if I take the shapes, are they are there ways or theories that would actually do the second point there, but within the space of physical allowable transformation? You know what I mean?
So he needs to
Yeah.
use the space, the shapes to hold of diffeomorphism to
Yes,
physically allow diffeomorphism.
exactly. That's. But is it? I mean, it's not highly non-trivial, of course. In this constraint.
It's talked about a lot.
Yeah, I'd say it's probably talked about a lot. Probably some sort of first attempts exist, but sort of in a robust manner. I'm not aware of that. Yeah. Okay. Let me comment about so computational anatomy and deep learning, which is sort of in fashion right now. And I think where exactly how exactly they'll be combined will be an interesting point, because on one side, what one happens here is one has small data sets. There is a finite supply of patients, a quite high-dimensional space of objects. They sort of put a lot of structure in there to get some information out. Whilst here, on the other side, you sort of you take your data and put it in a black box and see what comes out. And what comes out is often very useful. But now how you combine this sort of additional structure knowledge you put into there with neural networks and deep learning, I think it's, will be explored, I'm sure, in the next years. Yes, modeling uncertainty and noise with stochastic approaches, something, well, Daryl is definitely interested in this moment, and there'll be several talks about it next week. And, and also mathematical questions raised by it. We saw connections with partial differential equations or existence problems, properties of a geodesic distance function. So all that raised by these models that are used in biomedical applications are sort of a nice field for a mathematician to work in. Right, thank you. That's
All right, there were a lot of questions already. Are there any others?
Thank you for it. It was a very nice talk. I have a question. So people talk about shape, and they're usually related to a visual perception system, right?
right.
And that's normal, and that's what almost. Is there any other type of shape that come from higher space based on data that people study also, that apart from the shape that we observe, there are plenty of ways of organizing data in space, in higher dimensional or even lower dimensional space?
So similar approaches to what I've shown on curves.
Because what you've done is not restricted at
No,
all.
no,
to
it's not restricted.
Things that
So
look like shapes.
So related ideas are used in functional data analysis. So you just have one-dimensional signal over time. But if you have processes where sort of time alignment is where you don't necessarily have the same time points correctly aligned, for example, well, like people have growth spurts at different times. And so you can use the same things to just look at functional data. I saw briefly, actually, while I was looking at the talk, apparently some people took, well, no, actually, they took sort of star diagrams. So where they plotted data of years, sort of months along radial things to get something like that. And the data in question was milk production in New Zealand and the US of sort of how much milk do cows produce each month. And then you get a curve, which is a star shape, and they use the shape analysis technique to compare those things. I did not look in much enough detail to say whether they got anything useful out of it, but definitely an attempt was made. So Kendall's shape space was applied. So you don't need, if you have landmark points, say, to, for example, study whether, I think, settlements, if you just put a point on a map for each settlement, on a historical map, then you can ask yourself, how are they spaced? Are they sort of equally spaced out by comparing, is this triangle shape sort of in general, on average, equilateral? And yeah, it somehow comes from geographical distinction, but not necessarily a shape as an outline of things. Yes, I might think of other examples.
Any other questions? Yes?
Sorry about this. In Kendall's model, the number of points determines the dimension of the projective space used to model it. So if someone put one more point for the same shape, then it's in a different space.
So you need to have the same number of points on all the
So
objects
the
you analyze.
practitioners should agree on how many shapes are allowed to put for the on the shape on a sheep. Sorry, on a fish. Sorry.
Yeah.
Then to compare. Otherwise, if someone used the whole curve of the boundary, then it will be in the infinite dimension.
Well, you need to not just agree on the number, but you also need to say sort of how do you define each point? Because you need to find the same point on each shape that you want to analyze. So you sort of, for example, need to say like the point 8 is sort of the rightmost point on my skull. And then if I now look at 10 skulls, I can put point 8 on each one of them. And they will be sort of in biological correspondence to each other. Or I say point 1 is where the front tooth joins bone.
All right. So these
Jaw.
things are done manually.
Yes, landmarking is done manually, absolutely.
If you have a 3D scan of a big object, is that you have to hire some postgraduates to do
Yes.
this for months?
Yes, yeah. So 3D landmarking is I mean, landmarking in general is time consuming, absolutely. Which is one reason why automatic methods can be helpful.
For example, what kind of automatic?
Well, for example, if you represent the outline, as a curve,
Yes.
and you choose points on one curve and you match this curve to another curve, then you will get, the matching will give you a point-to-point correspondence, and you can propagate the points on one curve to the other one, and will give you automatically the corresponding landmarks on your other curve.
If I understand you correctly, the curves are all parameterized.
Sorry, when you work in the quotient space of if you work in this quotient space of unparameterized curves. So yeah, if you represent the one object as this infinite dimensional shape and you match it to another infinite dimensional shape, you will get a corresponding, geometrically a horizontal geodesic, which will also give you point-to-point correspondences. If you choose points on one shape, it will give you points on the other shape. However you choose points on the first.
But do you have a natural way of going from the continuous curve there to whatever discrete curve? I have 10 different skulls, and each of them come with a bunch of points for the outline that may vary from one skull to the other. Each of them defining a discrete curve.
Right.
So now it's a problem of discrete geometry, right? Which is not obvious. Discrete differential geometry.
But you better live in a discrete world because your images arrive pixelated.
Yeah. But the theory is in the continuum, and the theory
Yeah,
makes
well, the
good
theory
sense.
has to apply
But
to
you
the
want
discrete.
you want to have a
That's
side-by-side continuum, and you want to use the power of the continuum to make this kind of argument, and
That
you want to
means-
have a
that
discrete
means-
version of it.
That means sample, right?
Yeah,
sample
sampling.
of the object.
Yeah, I mean that
You-
depends on how you
you-
discretize these Riemannian metrics and the corresponding problem. For the H1 metric, you can use piecewise linear discretizations, and that works quite nicely. When we deal with second order metrics, what we use we do computations in the B-spline space, third order B-splines. And so we first, we take our discrete curve and we approximate it by a B-spline, and then we work in that space, and then we evaluate it again. Well, we plot the result in B-splines.
Do you have any kind of Hausdorff stability about your output? Which means if you sample two things, the same thing twice,
An answer.
right? Whatever you do, then the output would they be close or not? Because
yes.
this
Yes,
gives
we
people
have
some
some
confidence about the method, right?
we have some convergence results for our numerical methods.
If I turn the camera to 45 degrees and give you pixelated data at 45-degree orientation, you're going to get the same
What I
answer.
mean is, even for one curve, if you sample one way, then you get something. If you sample it again,
Yep.
the chance to sample the same point might be very small. Then whatever you get, you can say, well, the result will be close anyway. That will give people some confidence of what you have done.
Yeah, no, I mean, the theory tells you some stability results. Yeah, that what you do is continuous with respect to Sobolev topologies and the result. So,
Any other comments, questions, suggestions? All right, let's thank Martins again.